So welcome back again from the break. Let's look at the concept check question so we can keep moving. So how does the concept of descent with modification explain both the unity and the diversity of life? Well, if it's descent with modification, if we draw one of Darwin's tree diagrams, here is our common ancestor. If you have descent with modification, that descent means that you have individuals that start to accumulate their own unique features. And so we would have a branch point. So this might be two finch populations, one finch population on one island, one finch population on a second island. They're going to have to evolve or adapt their own unique set of features that allow them to utilize the environment that they're in. The individuals that arrive on the originally find an environment that they can utilize, but as they continue to live there and utilize those resources, individuals will spontaneously develop mutations that will allow them to better utilize those resources. And over time, the population will move in that direction. Given that these are individuals in two separate locations, they'll have their own different populations. So there's the diversity. This group and this group, or these two species, will be separate from each other. There's the diversity. But you'll know that they're descended from a common ancestor because there will be common features, and those common features reflect the fact that they both trace their origin back to the common ancestor. So descent with modification explains the diversity because each population that develops into a new species develops its own unique set of characteristics as a consequence of adapting or evolving to better suit the environment that they find themselves in. That's the origin of the diversity, by descent with modification. But by going up the tree, by going back to the branch point, back to the common ancestor, we can explain the unity, because their unity is a consequence of that common ancestry, the fact that they represent modifications of a common feature or set of features inherited from the original common ancestor. So that's how descent with modification or natural selection can explain both unity and diversity amongst life. So let's look at a couple of examples of natural selection as identified in the textbook. And there are many, many examples of natural selection that we could talk about. These are the ones that the book has identified, and there are new versions in the new version of the textbook. These are versions that have come out of the previous edition, but these are the ones that I like to talk about because I think they're pretty obvious. So one comes from Florida. It's a type of bug called the soapberry bug that came into Florida as a foreign invader and entered in through South Florida, through the Miami region. There are similar sorts of bugs in other regions around the world, and they have different beak sizes as a consequence of the type of fruit that they're feeding on. Where this becomes important in Florida is, and I think I've got a diet, is that the point at which they entered Florida in South Florida, they started feeding on a particular type of fruit, and as a consequence of feeding on that fruit, the beak of the bugs adapted to that type of fruit, and it reflects a particular size, particular length of beak in order to be able to access the liquids that the bug is sucking out of the fruits. And if you look at the examples that are preserved in the Natural History Museum of Florida in Gainesville, you can see that there is a distribution of beak size that reflects feeding on the particular type of fruit that the bugs were feeding on in South Florida. As the bugs moved northwards into Central Florida, they accessed a different type of fruit. And as a consequence, the beaks started to change. So here's the average beak length as represented by the specimens in the Natural History Museum. Note that the beak length has got smaller. That's because it's easier for the bugs to penetrate into the fruit. They don't have to go as deep into the fruit to get access to the liquids that they're sucking out of the fruit, so they don't need as long a beak. And so individuals with the shorter beak are now able to thrive and survive, and having a long beak, because it represents an expenditure of more resources for very little advantage, you can feed just as well with a shorter beak. Those individuals with the longer beak disappear because the long beak now turns out to be a disadvantage cost benefit wise compared to a short beak. So here's an example of where a feature changes as a consequence of the energy investment necessary to maintain a feature when really you don't need to. You can get by with a shorter beak and still feed quite comfortably because you're utilizing a different resource, a different food resource. That's natural selection. Then we know that one of the big issues with antibiotics and bacteria is that bacteria are becoming more resistant to antibiotics. One of the big ones that is of huge significance is MRSA, methicillin-resistant Staph aureus, Staphylococcus aureus. The reason why this is such a big deal is because becoming resistant to a single antibiotic, methicillin, means that it has become also resistant to about 5 or 6 other antibiotics as a consequence of this. So in fact, what was once known as methicillin-resistant Staph aureus is now known as multiply resistant Staph aureus because it's resistant to multiple antibiotics. This is the so-called golden staph. When you get infected by this, it is very, very difficult to get rid of it because there are very, very little remaining antibiotics that we know are effective against this bacterium. So getting infected with this bacterium for many people is tantamount to a death sentence because you simply cannot cure these bacteria. And this is becoming a widespread problem, the resistance of bacteria to antibiotics. So why are they becoming resistant to the antibiotics? Because the antibiotic represents a selective pressure. It will kill them if they are not resistant to it. So where does that resistance come from? Well, it develops spontaneously as a result of mutation. And so when we utilize antibiotics, what we need to remember is that whatever an antibiotic works against bacteria, it's because the bacteria have yet to develop or to develop, I guess, a spontaneous mutation that gives them resistance to the antibiotic. But it's only a matter of time and exposure until one of the spontaneously occurring mutations that occur all the time will actually give a bacterium resistance to an antibiotic. It may be complete resistance, it may be a limited resistance, but nonetheless, it starts to give the bacteria resistance to the antibiotic. And that antibiotic now becomes less effective. And so when we want to look for the reason why antibiotic resistance is occurring in bacteria, we look no further than our own use and, more importantly, misuse of antibiotics. We don't use them under the right circumstances. We don't use them in the right way. We tend to not use them for the length of time that we ought to. We tend to use them in situations where we really should not use them. And a lot of this antibiotic resistance has developed not because of necessarily human consumption of antibiotics, but because we tend to use antibiotics in agriculture to prevent to prevent bacterial infection, particularly in cattle and in poultry, which are notorious for getting infected by bacteria. And by using antibiotics to prevent these infections and therefore to promote the rapid growth of the animals. We're simply providing more opportunities for the bacteria to be exposed to the antibiotics and providing conditions that will automatically select out individuals who have a partial or complete resistance to the antibiotic as a consequence of a spontaneous mutation. Those mutations must be present prior to the exposure to the antibiotic, not after. Because remember, if they don't have the resistance, they're going to be killed by the antibiotic. So the resistance, the mutation, must be present before they get exposed to the antibiotic. What the antibiotic does then is kill off all the bacteria that lack that mutation and leave behind the antibiotic-resistant bacteria, because they're not going to be killed by the antibiotic. Those then reproduce, and the numbers of antibiotic-resistant bacteria increase quite dramatically very quickly as a consequence, because we know bacteria reproduce really quickly. What is even scarier is that bacteria, as you'll learn in chapter 28, can pass this genetic resistance to antibiotics between other individual bacteria of the same species, but also between individuals that are members of different species. And so bacteria can become resistant to antibiotics without ever having been exposed to the antibiotics by gaining the genetics necessary to be resistant to the antibiotic from a strain of bacteria that already is resistant. And remember, we are the primary cause for the development of this resistance. Something to think about. So, another quick concept check. I don't think well, you could use this as a break if you want. I will stop the recording and then start it again, so we can treat this as a real break if you didn't take one earlier. So here's our concept check question. Why is the statement antibiotics have created drug resistance in MRSA inaccurate? I'll see you on the other side of the break with the answer.